Hi, this is Alex from devstories.eu. AlphaFold, Protein Structure Prediction, episode 21 of 21. For years, the industry assumed that predicting a protein structure required incredibly specialized custom neural network designs. You needed multiple sequence alignments, explicit pair representations, and computationally heavy triangular updates just to get a viable result. But what if a standard generic transformer could do the exact same job? The answer is a concept called flow matching with SimpleFold. The SimpleFold paper by Apple introduces a radical departure from the rigid architectures we have seen in traditional folding models. It strips away the domain-specific heuristics entirely. Traditional models hard-code biological intuition into the network. They use multiple sequence alignments to find evolutionary clues and triangle updates to enforce geometric rules. This requires massive compute and highly specialized engineering. SimpleFold abandons these mechanics, opting instead for a flow-matching generative model built exclusively on general-purpose transformer blocks. SimpleFold treats folding as a conditional generative task. Think of text-to-image models, where a text prompt guides the generation of a picture. Here, the amino acid sequence is the prompt, and the output is the all-atom three-dimensional coordinate structure. It achieves this using flow matching. Flow matching generates data by defining a continuous path from a simple noise distribution to a complex data distribution. During training, the model learns a time-dependent velocity field. It integrates an ordinary differential equation over time, gradually moving random noise toward the true atomic coordinates. The process starts when a frozen pre-trained protein language model, specifically ESM2, converts the input amino acid sequence into a sequence embedding. At the same time, an atom encoder takes noisy atomic coordinates and processes them into atom tokens. Here is the key insight. Instead of maintaining complex memory-heavy pairwise interaction maps, SimpleFold uses a grouping operation. It simply averages the atom tokens belonging to the same residue into a single residue token. These residue tokens are concatenated with the sequence embeddings and passed into the residue trunk. This trunk contains the bulk of the model parameters. It is made up entirely of standard transformer blocks with adaptive layers conditioned on the flow time step. There are no geometric equivalent modules and no triangular math, just standard attention and scaling operations. Finally, an ungrouping operation broadcasts the updated residue tokens back to their individual atoms. An atom decoder then predicts the velocity field to update the final atom positions. During training, the system does not sample time uniformly. It heavily oversamples time steps closer to the clean data manifold. Because protein structures have a strict coarse-to-fine hierarchy, this late-stage focus forces the model to learn highly refined structures, including delicate side chains. Furthermore, because the model uses a generative objective rather than a deterministic regression objective, it naturally captures uncertainty. If you pass the same sequence through SimpleFold multiple times, it can generate an ensemble of different valid conformations, accurately reflecting how proteins actually move and exist in nature. SimpleFold proves that if you map the problem correctly, a general-purpose transformer can learn the underlying physics of protein folding directly from the data. I encourage you to read the paper, explore the official documentation, and try running the code on your own hardware. You can also visit devstories.eu to suggest topics for our next series. That is all for this one. Thanks for listening, and keep building.